So last week we focused on work energy theorem, okay, which the basis of which was kind of review from Science 10, but obviously we took it to another level, okay, where we were looking at situations where both kinetic and potential energy were changing because of the work being done, okay. What we're going to look at today is entirely review of Science 10, okay, and there's going to be nothing added to this that you didn't do in Science 10, and that's the law of conservation of energy. Okay, if you're remembering like problems that you would have done to do with this, they would have been like roller coaster questions or people going down hills on sleds and things like that. Okay, the difference between a law of conservation of energy problem or situation versus a work energy theorem situation is this. In a work energy theorem situation, there is a change in energy, okay? That means that there's a final energy and an initial energy, and they are different because energy is either being gained, work is being done on the system, or energy is being lost, work is being done by the system. In a law of conservation of energy question, no work is done. So EI and EF are equal. Okay? Now, the trick is that these questions give you very similar types of information, and it can be difficult sometimes to tell them apart. Okay? So, what are some things, do you suppose, that a work energy theorem question would say or give that might be different from a situation where no work was being done? Or maybe let's look at some things that might be similar. In a work energy theorem question, what's the other way to calculate work? Force times distance. You will never get either one of those in a law of conservation of energy question. The only force doing anything in a law of conservation of energy question is gravity. Okay? Gravity is converting the potential energy at the beginning into kinetic energy at the end. Okay? Or vice versa, it's turning kinetic energy into gravitational potential energy if the thing is going uphill. Okay? But there's no work being added. So as a result, there are no forces other than gravity. There'll be no friction. Okay? There'll be no applied forces or anything that could change the energy of the system. Okay? So if you see a question and it's talking about force, it is a work energy theorem question. Okay? If it uses the word work in any context other than no work is done, okay? If it uses the word work, it gives you work or asks you to find work, then it's a work energy theorem question. Okay? A law of conservation of energy question doesn't have any work in it, so that word shouldn't even appear there unless it is to specifically say no work is done. Okay? Everybody follow me there? Right? So there are some differences, but there's a lot of things they give that both will give you. They'll both give you heights. They'll both give you speeds, okay? Because they both deal with mechanical energy. Okay? The difference being, in a conservation of energy question, the mechanical energy doesn't change. How much of it is kinetic and how much of its potential does, but the overall mechanical energy doesn't change. In a work energy theorem question, the overall mechanical energy does change. And that's what we have to kind of be on the lookout for. Okay, so key points for the law of conservation of mechanical energy. First off, energy cannot be created and it cannot be destroyed. That is the law of conservation of energy stated in words. Okay, EI equals EF is how it's stated mathematically. That is how it is stated in words. Okay, understand that energy can be converted from one form to another. Okay, that doesn't mean work is being done. As long as the final energy and the initial energy are equal, and they're being converted into each other at 100% efficiency. Okay? And then lastly, use this concept to calculate other variables related to the mechanical energy of an object. So I give you a roller coaster question, I tell you it starts on a hill that's 50 meters tall, moving at 3 meters per second, and I ask you to calculate how fast it's going at the bottom. Okay? Something like that. You would have done that in Science 10. So it may, right now that you might be going, oh, I've never heard that before, but once we do one, it'll probably seem familiar. Okay? All right, now, with the law of conservation of mechanical energy, there is something we have to understand about this. Nothing ever works this way. Okay? This is an idea, kind of an ideal world, perfect physical world, okay, utopian physical world kind of situation. Okay? There is never a case in the natural world where the energy is 100% converted from one form to another. Energy is always lost when energy is converted from one form to another. Okay? And that's usually because of what force? Friction. Because friction's always there. Okay? Something is always going to cause some energy to be lost. So we talk about this from a fundamental perspective. Okay? All right. So there's two kinds of energy. We talked about those on Friday. Okay? Kinetic and potential. And when we add them together, we get the mechanical energy. We've already gone over that in work energy theorem, so hopefully that sounds familiar. Okay? The total mechanical energy is EK plus EP. Okay? It also means that if there are any non-conservative forces, friction is the most common non-conservative force, okay, that it may appear to cause a loss of energy from the object. Okay? And that can be calculated using this formula, which is what we were using last week when we did work energy theory. Okay? Work is the change in mechanical energy. Final minus initial. Okay? Here's our final mechanical. Here's our initial mechanical. That's the formula we use. If we're in a situation where we're dealing with the law of conservation of energy, when I subtract these two numbers, what will I get? Right, I get a big goose egg, right? Because they're equal. Right? If I subtract them, they'll be equal. Right? They'll be zero, sorry, because they're equal. All right, so if we're dealing with a roller coaster situation, which is the most common one, okay, if we start up at the top of the first hill, if we're dealing with a standard roller coaster, okay, you're towed to the top of the first hill by a conveyor, and then you're released. Okay, and you, at that point, would have lots of potential energy because you'd be very far off the ground, but not very much kinetic because you're not moving very fast. The conveyor, moves at 1 or 2 meters per second. Okay? When you get to the bottom, you would be at your minimum potential energy, but your maximum kinetic, which means at this point you'd be moving very fast. Exactly. Okay? And if you go over another little bump or something, you get a little more potential, you'd slow down a little bit, so your kinetic would be a little bit less. Everyone okay with that idea? Okay, you've all been on a roller coaster before?
Wait, sorry, why is the maximum potential energy at the bottom, not at the top?
It's maximum kinetic is at the bottom. Minimum.
Oh, it's just minimum.
Minimum
sorry.
potential at the bottom. Yeah.
Okay. That makes sense.
Okay. All right, so with a roller coaster, that's generally how it works. There are exceptions. Some of the more modern roller coasters actually make it more fun by shooting you out of the starting point at a high rate of speed. Okay, and that, of course, makes it a bit more exciting. So you have some kinetic energy to start with instead of building anticipation and towing you up the hill, okay, like they do on the Mindbender. We had one particular one on the Mindbender one year where myself and Mr. Dickey were on there with a couple of our students, and they towed us up to the top, slow like always. And we got to the top, and just before we were going to go over the first hill, the brakes came on. We're like against our harnesses, staring down the drop and not moving. And we're like,
Why they put the brakes on?
this is not fun. We don't know. And nobody ever said why. We just sat there against our harnesses for what seemed like a really long time, but probably wasn't. You know how that works, right? Your perception of time changes. Okay, and the kid beside me, he's in like full-blown panic mode. So am I, but I'm trying not to show it. Just beads of sweat and whatever. And he's freaking out. And then he's like, "I'm getting out." I'm like, "What?" And he's pulling a full-on like Mel Gibson. I'm dislocating my shoulder to get out of this thing. Like, he is like he's got the belt off and that thing that goes over your neck. He is like squirming and he's halfway out. I'm like, "Where are you gonna go? What, are you going to jump? Like, you're better off to stay in here. Like, get back in," and then holding him, and put your belt back on, and then just as I'm, like, getting finished, kind of, get your belt back on. He's like, "But there's stairs over there." I look over. There's stairs over there. There's, like, a walkway and stairs, probably for maintenance. But there's no way we can get to it. Like, what are you going to do? Are you going to crawl along like Spider-Man? Like, it's not going to, and just as we're getting to that point, they release the brakes. Never a word over the speaker as to why we were stopped. It was the quietest Mindbender ride I've ever been on. Everyone was too scared to scream because we had no idea whether we were going off the tracks or not. Because the Mindbender did go off the tracks very early on because they assembled it wrong. Okay? It was a big thing. Like several people were killed. The maximum length of the train is 3 cars. They put 5. Seems like a simple thing to follow instructions. This is the importance of following instructions, by the way. Okay? But they put 5 cars on the train. So there's a lot of whipping action. If you've ever ridden the Mindbender, it's gone now. They're taking it down, actually. Okay? But if you're in the back car, it's a totally different ride than the front car. It whips quite a bit more. And they actually had, for a while, the back car backwards, which was really cool because you couldn't see anything coming. But anyway, they had 5 cars in there, and the whipping action actually caused them to fly off the track. Yeah, it's scary. Anyone want to ride a roller coaster now?
No.
You know what's even scarier? When they pull everybody off, put sandbags on the thing and run it.
What?
Seen that too. Yeah. You're like watching these sandbags ride around, and you're like, I'm not a human sandbag. I'm not getting on that thing. Nope. But it's coming down now. They're taking the whole thing down. Somebody else bought out the park or something. So
What park is it at?
Galaxyland at West Ed?
Oh, okay.
Yeah. But they're redoing the whole thing. Okay. Making sense there? Sorry, I got sidetracked. All right, so in other words, our final mechanical energy is equal to our initial mechanical energy. So that means the total mechanical energy remains constant along the entire path between the initial and final points. It never changes. Okay? So if we were watching this car go down this hill here, okay, at its initial point, all of the energy would be potential, and none of it would be kinetic. We'll say it's not even moving yet. Okay? And the total mechanical energy line would be full. Okay? When it gets to this point on the line, okay, what do the kinetic and potential lines look like?
They'd both be in the middle.
Yeah, probably close to the middle. They'd be close to equal at that point. What does this one look like?
Full.
Full. Does this one ever look anything other than full?
No.
No. Okay, that line stays full all the time. All that happens is these go up and down, okay, as it changes into each other. Okay, when it's at a higher point, it's more potential, and at a lower point, it's more kinetic. Those two just flip-flop constantly, where the total mechanical energy bar stays totally full all the time. Okay? All right, everybody okay with that? Okay, now, you guys already know I'm a nerd. We were clear on that, and I'm okay with that. You can say Coder is a nerd because I know who I am and I'm comfortable with that. Okay? I used to coach track and field, and in Edmonton at Foot Field, their track and field facility, they have this device. It's a shot put return device. That's not the exciting part. Okay? So if you put a shot put, regardless of which size, at the top of this ramp, and let it go. Don't push it, just let it go. It rolls down the ramp. That's not the exciting part, because obviously it rolls down the ramp. Okay? But as it rolls along this length of flat rail, what happens to it? It slows down. Okay? Every single shot put comes to a stop right at the end of the rail. Every one. Doesn't matter what size. Okay? What they did is they designed this thing so they would know how much work would be done against friction along the length of the track, and made sure they made a ramp that would provide that much potential energy, so that it goes down the ramp and then it converts all of that energy into, all that mechanical energy into heat and sound and whatever, and when it gets to the end, it stops. Okay? So I saw this, I've watched it a few times, I'm like, no way. Every single time it comes to a stop, I go grab the whole track team. You have to come see this! And they're like, what? I just show them this, and the guy rolls up, like, see? I'm like, what? You just don't appreciate this on the same level as me. Because you're such a nerd. Yes.
Do you have a video of it?
Huh? I don't have a video of it. I took this picture back before phones really did that.
Okay.
Yeah. I should have got a picture more recently, or a video. Okay. But yeah, it always worked. Simple application of physics. I found out later they actually had this designed and fabricated by the Faculty of Engineering at U of A. Okay, so these guys actually did all the calculations and fabrication. Yeah, so it's pretty cool. It actually works out. So if you ever think what you're learning here isn't going to be applied somewhere, there you go. It can be. All right, so the principle of conservation of mechanical energy tells us that, yes, energy can always be converted into other forms, okay, and that it's never created or destroyed. Is it always doing useful work? No. Some of it's going to be lost, but we can always account for it, okay? Even if it's not going to stay as mechanical energy, it'll become sound, it'll become light, it'll become heat, okay? But that energy is always accounted for. So basically that means the amount of energy in the universe is constant. Yeah, it's just always being converted from one form to another. Okay? That's part of the whole idea of like the expanding universe and then the contracting universe, and that there may be a cycle of expansion and contraction in the universe that would eventually lead to the big crunch. The Big Bang causes everything to go outwards and expand. The big crunch is when that goes the other way. We won't be around for that.
So after it's reached its peak of expansion, would it collapse in because the energy would be too dilute? Or?
Yeah, it's kind of beyond my understanding, but there's something to do with the different fields and all these particles that they theorize to exist, like the Higgs boson and things like that, that dark matter and all that stuff that can create gravitational forces that are kind of beyond our comprehension. It's an interesting idea. Okay? Rather than it'll all just continue to expand until it fades to nothingness. I don't know. The whole thing of birth and rebirth, it's sort of refreshing, I guess. Okay, so here's another unfortunate but real world application of this stuff. Okay. Back when we hosted the Winter Olympics in Vancouver, 2010? Okay. On the very first day of practice runs for the skeleton, one of the athletes was thrown from the track and killed. Okay. And they hadn't really anticipated the conditions that they were going to have. It rained, and the track, of course, is just a big, ice tunnel, basically. Okay, but they do that by having cooling lines, kind of like how they make an ice rink. Okay, same process, cooling lines running along. And it had rained, which had lowered the coefficient of friction significantly on the track, okay, beyond what they had kind of anticipated. And as a result, the athlete got going a lot faster on one of the corners than they had ever anticipated anybody going, and they hadn't built the corner high enough. So he went out the corner and was killed. So short of having to do something that would lower the coefficient of friction, because they didn't want to throw debris on the ice to slow things down, what do you suppose the simplest solution to having people not go so fast on that corner would be?
A dome over it so it can't get affected by rain.
Again, they couldn't really change those parts of the track. Like building a dome, I mean, it's already that slippery, right? He went over that corner because he was going too fast. He had too much what? Too much kinetic energy. So how do you make sure somebody doesn't have as much kinetic energy at that point?
More potential.
Okay, or
Less kinetic.
less kinetic at that point means less potential where?
At the highest point.
So how do you make sure you have less potential at the beginning?
Start
it lower. Okay, simple application, right? Simple application of conservation of energy, work energy theorem. If people are going too fast in that corner, you don't let them have as much energy at that corner by having them start lower, where they would have less total mechanical energy to begin with. Okay, that was the solution they came up with. Okay, so instead of starting up here, they started down there. Okay, less total mechanical energy. Okay, now as you can see, this is kind of a better graphic of that thing we looked at before, where the total mechanical energy, regardless of where they are on that track, is always 600,000 joules. Okay? How much of it is potential and how much of it is kinetic is always changing. The kinetic is always going up as you go down the hill, and the potential is always going down. All right, everybody okay with that idea?
Yeah.
Is that ringing a bell from last year? Okay, so we're going to try this. Did I show you the Evel Knievel going over? I did, in
Sure.
projectiles, right?
Oh,
Going
yeah.
over the Grand Canyon, right? So we looked at that from a, did I show you that? Evel Knievel jumping the Grand Canyon?
I don't remember.
I remember someone driving off the Grand Canyon, but that's it.
Oh, that was Thelma and Louise. Okay. I'm pretty sure I showed you. Okay, so if we're looking at this situation here, again, we're gonna say, sorry, Tom?
I was just gonna ask, would it not be maybe, I was just thinking about it, smarter to jump from the lower side to the higher side? Because as you're going up and you land, you wouldn't be going down as much, where if you're going from the top, gravity's pulling you down for a longer amount of time, so you hit the ground harder, wouldn't you?
The only worry is if there's a significant height difference, and there really wasn't a really significant height difference in that jump, but if there's a significant height difference, you're not going to have enough energy to get to that
Right.
level, right? At least this way, even
Yeah.
if you botch the takeoff a little bit, you've got the advantage of I'm falling as opposed to I'm trying to fly. Right? I'm trying to
But if
climb.
you did make it, it wouldn't hurt as much, right?
You would be going slower, yes.
Okay, yeah.
The other part of that too is if you're landing on a higher thing, you still need to get higher than it
Yeah.
to land on it and be coming down, right? So. Okay, so we're gonna assume that this is in the perfect physical world where no energy is lost to friction, no work is done against non-conservative forces, which means that our initial mechanical energy is equal to our final mechanical energy. Okay, how do we calculate mechanical energy?
EP plus EK.
Right. Okay, so we're going to say that the initial potential plus the initial kinetic equals the final potential plus the final kinetic. Okay, are any of those numbers going to be zero?
Yeah.
So we're starting here at a height of 70 meters, so we have initial potential. Okay? And we're moving at 38 meters per second, so we have initial kinetic. Okay? When we land, we're still 35 meters above the bottom of the canyon, so we still have some potential. And they're asking to calculate the speed, which we already established would be faster. Okay? So we definitely have all four of those kinds. None of them are zero. Okay? So now, what I would do is I would isolate whichever one of these energy types has the thing I'm looking for. Since I'm looking for VF, I want to keep EK final on that side by itself because VF would be part of that. That means I need to move the potential energy final over to this side. How would I do that?
Minus it.
Yeah, just subtract. Okay, so I'm going to have EP initial plus EK initial minus EP final equals EK final. Okay, now I can put in my formulas. I can expand it out again. Okay? Sometimes it's easier to do that subtraction operation before you've got the M's and G's and V's and everything in there. Okay? So I got M times G times H initial plus 1/2 MV initial squared minus minus MGH final equals 1/2 MV final squared. Okay, do I have something that is in every term?
M.
If it's in every term, what can I do with it?
Take it off.
Yeah, I can cancel it out. You don't have to, you can leave it in, okay? But in this case, I don't think I ever gave you the mass of the motorcycle. I didn't. So, we have to cancel it off. We don't know what it is. Why can I cancel it off? Seems like it's important because mass is part of energy. The bigger something is, the more energy it has. It's the same throughout, and what's the only force that's causing the mechanical energy to convert from potential to kinetic? Does gravity affect all things equally regardless of their mass? That's why you can cancel the mass. It wouldn't matter. The final speed of this motorcycle is not dictated by the motorcycle. Any object that does this exact same motion will be moving at that speed because gravity affects all things equally. Okay? Everybody okay with that? Right. Now, does that mean that if I did this with a basketball that the energy would be the same? It does. We're just talking about the speed. If I'm being asked to calculate energy, I've got to have mass. But in this case, I'm not. I'm only being asked to calculate a height or a speed. In that case, mass doesn't matter. Okay? All right, so I'm going to cancel off all the m's. Okay, I want to get VF by itself. What do I have to move?
1/2.
The 1/2. What do I do to do that?
Divide it.
Yep. Okay, so I divide both sides by 1/2, and then, yep, I got a square root. Okay, so if I'm plugging in all my numbers here,
So do you do gravity times height?
yep. Okay, so that first one, gravity times initial height, so that's going to be 9.81 times 70, plus 1/2 times 38 squared, that's my initial speed, minus 9.81 times 35, that's my final potential, okay, divided by 1/2. Okay, but now, when we look at this, was that like a super complex algebraic manipulation? There's a bit of stuff to do there, but I mean, it's not terrible. Some of the work energy theorem stuff we've done was more involved than that. Okay, so we are gonna have 9.81 times 70 plus 1/2 times 38 squared minus 9.81 times 35. Okay, divided by 1/2. Square rooted. Okay, well that fits. We did say they would be going faster on the other side. Okay, in this case, 46 meters per second. So, just for reference sake, that's 166 kilometers per hour. I wouldn't want to try and control a dirt bike at that speed. Especially after falling 35 meters, which he didn't fall, obviously. But yeah, anything really. It's tricky.
Wait, why did we times your answer by 3.6?
Oh, I was just showing you what it was in kilometers per
Oh,
hour.
okay.
Yeah. Okay, so the answer in meters per second ended up being 46, what do we have? We had 3 significant digits, so 46.2 meters per second. Okay, and with conservation of energy questions, you're either going to be asked to calculate an energy, a speed, or a height. Okay, so it might say, what's the final kinetic energy? Well, then you have to calculate the final EK. Okay, what's the final height? So you calculate HF. Right? There's not really a lot of variations for a conservation of energy question. A work energy theorem question, there can be lots of variations. Okay, but with a conservation of energy question, those are really the 3 things: a height, a speed, or an energy. And I don't remember the last time I actually asked someone to calculate an energy on a test. Okay, it's almost always a height and a speed. Okay, so that's all the stuff we just did. Okay, let's have you guys try this one. Okay, it's a little bit different because they actually do ask for the energies in this one, okay, as opposed to a speed or a height, but it's still good to kind of just go over. It's actually quite a bit easier than the one we just did. Okay. All right, so we got a frictionless roller coaster car that's 800 kilograms, and at one point on its journey, this car has a speed of 4 meters per second and is 35 meters above the ground. Later, its speed is measured to be 20 meters per second. Okay. Calculate its total initial mechanical energy and its gravitational potential energy in the second instance. So if we're being asked to calculate the total mechanical energy, okay, it says initial here. Does it need to say initial? It could just say, what's the total mechanical energy? Because that value is not going to change. Okay, so initially at least we have enough information to do it, right? So we can just go, okay, mechanical energy equals m times g times h initial, our initial potential, plus our initial kinetic, 1/2 mvi squared, right? So we take our 800 kilograms, we multiply it by 9.81, and then we multiply that by 35 meters. And we add that to 1/2 times 800 times 4 squared. Okay, why did I not cancel the masses on this one?
It's not in F.
It's what?
No, it isn't. It's in
Well, it's not in this term, so I couldn't cancel it there, but also if I'm gonna calculate energy, is mass part of that? Yeah, I can't cancel my kilograms, or I don't get kilogram meters squared per second squared, or joules. Okay, so I can only cancel the mass if I'm looking for a speed or a height. Okay, because then it's just gravity doing the acceleration, and it's only dependent on gravity, not on the mass. Okay? In this case, energy is partly dependent on the mass. All right, so we're gonna have 800 times 9.81 times 35 plus 0.5 times 800 times 16. Okay, so we got 281,080 joules. Okay. Now, it says here that what is the gravitational potential energy in the second instance? Okay, do they tell me the height when it's moving at 20 meters per second? But with that 20 meters per second, can I calculate the kinetic energy? Yeah, and since I already know the mechanical energy, I just calculated it, can I get the potential using those two numbers instead? I can. I just go back to this formula here, okay, and I say mechanical energy, that number I know, okay, is EP plus EK. And while I can't use MGH to solve for this because I don't have the H, I can use 1/2 mv squared and solve for this. So I know this one and this one, I can use them to solve for EP. All right, so I take my 281,080 joules of mechanical energy that I just calculated and subtract EK, which will be 1/2 times 800 times 20 squared. That'll leave me with whatever potential energy is remaining. Okay? So I'm just manipulating this formula to solve for EK. So I'm going to take that number, my mechanical energy, which we said isn't going to change, and subtract 0.5 times 800 times 20 squared. Okay, so there's my remaining potential energy, 121,080 joules. Okay? Now, just so you know, on a test, I will not give you a conservation of energy question without the mass. Okay? So even though if you were solving for a speed or a height, you wouldn't need it, I will always give it to you. Okay? Because sometimes people don't like to cancel the mass, they want to have a number there. Okay? And I made this mistake once on a test. I forgot to put the mass on there. And I had people coming up to my desk asking me what the mass was. And I thought it would be funny if I gave them all different numbers. Because it didn't matter, right? It doesn't matter what number I give you. If you're solving for a final speed, you'll get the same number anyway. And so the first person came up and they're like, Mr. Craig, I think you forgot to put the mass on here. I'm like, oh yeah, it's 500 kilograms. Oh, okay, I'll sit down. And the next person comes up, Mr. Craig, what's the mass of question 5? 2,000 kilograms. Okay, go sit down. And then another person came up, and I told him like 10,000 kilograms. And then I start hearing chuckles, and I look out, see people chuckling, and I see some other people whose eyes are like dinner plates. And I'm like, oh, that wasn't as funny as I thought it was. Some people didn't realize what I was doing, and they didn't realize it didn't matter which mass they got. So from now, after that, I always put out what the mass is on there so that nobody gets panicked, because I ended up having to say, look guys, the mass doesn't matter. Just pick whatever mass you want, put it on there. I forgot to put the mass on the test. Okay. That one make sense? Okay. I'd like you to try number 2 before we do number 3, because number 3 is going to involve us actually using a little bit of projectile motion stuff to help us out. Okay, so just try number 2 for now. All right, so we've got a roller coaster. Okay, looks something like this. Okay, it's not a roller coaster. It's just being dropped. Sorry, not a roller coaster. being dropped. Okay, so it's gonna fall off a cliff like this. Okay, and it is above the ground with 36, moving at 36 meters per second. So our initial is 36 meters per second. The mass is 225, but we probably won't, its initial height is 225. Its mass is 55, which we probably won't need. Okay, use conservation to calculate its velocity when it reaches a height of 115 meters. So, okay, that would be down here somewhere. We're looking for VF when HF is only 115 meters. Okay, so it says use conservation of energy, so we should probably do that, okay, especially if the question tells us that. By the way, that's something always to watch for, right? Sometimes I do that on a question too. Solve this using this method. That usually means there's more than one method, but I'm testing this method right now. Okay, so always make sure you do it the way that is requested. All right, do I have initial potential energy in this situation?
Yes.
Yes, I'm 225 meters above ground. Do I have initial kinetic energy in this situation? Yes, moving at 36 meters per second. Okay, do I have final potential energy in this situation? Yes, still 115 meters off the ground, and they're asking how fast I'm going, so obviously I still have some kinetic energy as well. Okay, I want to solve for VF, which is part of that term there. So I'm going to move the EPF over, just like I did in the example we did a few minutes ago with the Evel Knievel. Okay, now I can plug in my formulas, right? So that's going to be M times G times H initial plus 1/2 MV initial squared minus M times G times H final equals 1/2 MV final squared. Again, mass is in every term. I'm being asked to calculate speed, which is not dependent on mass. It is only dependent on gravity. Okay, so I can cancel the masses. You don't have to if you don't want to. You could plug 55 in every time there's an M and you'll get exactly the same answer. Okay, so I want to solve for VF. So I divide both sides by 1/2 and square root that. Okay, so VF is going to equal the square root of 9.81 times 225 plus 1/2 times 36 squared minus 9.81 times 115 divided by 1/2. Okay, well that fits. It was moving at 36 meters per second initially, and it's further down now, so it should be going faster. Okay, at 59, actually we have 3 sig digs, so 58.8 meters per second would be our final speed. Okay, is that ringing a bell? Now, here's the tricky one. Okay, so I got a human cannonball, and they're being shot out of this cannon at 21 meters per second at an angle of 20 degrees above the horizontal. Okay, that platform that the cannon is on is 15 meters above the ground. Okay, if the acrobat has a mass of 56 kilograms, what is his gravitational potential energy relative to the ground when he is at his highest point in the flight? Okay, there's a couple of things we have to do here in order to get this answer. One of them has to do with projectile motion. Okay, how fast am I moving vertically at the highest point in my flight? 0. Am I still moving horizontally though? Okay, now here's the other thing. In energy is scalar. We use speed, not velocity. Why?
Horizontal and vertical components.
Well, there's horizontal and vertical components, but does my direction make any difference for the kinetic energy? It doesn't. Kinetic energy is only dependent on how fast I am going, not which direction I am going. Okay, so here's the thing. I often ask questions like this. So if a plane is flying along and it's going to drop a bomb, okay? When it drops the bomb's speed is the same as the plane, agreed? Does it matter that it wasn't moving vertically at time 0? No. It just matters that it was moving. The bomb had kinetic energy because the plane was carrying it. Okay? People forget that sometimes. When I ask that question in the context of a conservation of energy question, they go, oh, well, the bomb wasn't moving vertically, so it didn't have any kinetic energy. Oh, yes, it did. Okay? It only matters that it's moving, not that it's falling, okay? That it's moving. So, the human cannonball at his highest point still has kinetic energy, doesn't he? Because he's still moving horizontally. Does the horizontal velocity of a projectile ever change? It doesn't. So could we calculate how fast he's going at the highest point using our projectile motion thing that we used to do, right? Where we found the vertical part and the horizontal part. Okay? Let me give you a few minutes. This one's a bit of a thinker. Okay? So there's two parts here. Find the potential energy here and the speed at which he'll land when he hits the net, which is still 2 meters above the ground. That part's probably the easier of the two. Okay? You don't have to do any projectile stuff to do that part. Okay? You do have to do a little bit of projectile stuff to do part A. Yeah. Okay? If you get stuck on part A, do part B, come back to part A. Okay, so looking at part B, okay, I just want to calculate how fast they're going down here, right? And I'm going to use the law of conservation of energy to do that. So I'm going to have EI equals EF. We've got all four kinds of energy, both kinetic and potential at both points. Okay, so we can say EP initial plus EK initial equals EP final plus EK final. Right, so we know all of that. We're looking for the final speed, which is part of this, so we're going to subtract EP final over to the other side, just like we did in the example and in question number 2. Okay, then we're going to put in our formulas, so we'll have M times G times H initial plus 1/2 MV initial squared minus MG H final equals 1/2 MV final squared. The mass doesn't matter. Gravity is doing all the work to change the speed. Okay, so I can cancel that off, divide both sides by 1/2 and square root, and I'll have VF. Okay, now the initial height they told us is 15 meters. The diagram shows that. Okay, so I'm just going to put in 9.81 times 15 meters plus 1/2 times my initial speed. What's my initial speed? 21 meters per second. Does it matter that it's 20 degrees above the horizontal? Doesn't, because kinetic energy is scalar and only cares how fast you're going, not what direction you're going. Okay, so I can put in the 21. Okay, and then I'm going to subtract 9.81 times the 2 meter height of the safety net. Okay, divide that all by 1/2 and square root it, and I'll get my speed. So 9.81 times 15 meters plus 0.5 times 21 squared minus 9.81 times 2 divided by 1/2. Square root that. Okay, so when they hit the safety net, they'll be moving at 26 meters. Actually, we don't use the 20. 26.4 meters per second. Okay, so I didn't need any of the projectile motion stuff to do part B. Okay, now, questions on part B? All right. So the thing that's different for part A is that I need to know the horizontal component of this 21 meters per second, 20 degrees above the horizontal, because that's the speed the human cannonball is moving at their highest point, when they're only moving horizontally. Okay, so in order to calculate that, I gotta just find the horizontal component of that projected speed. Right, since it's the adjacent side, okay, it's just gonna be the cos of 20 times 21, okay, to get the speed there. Okay, to get v horizontal. All right, so cos of 20 times 21. All right, so they're moving at 19.7 meters per second when they're at their highest point in the flight. Now I can use that number to calculate their, what did they want here? The gravitational potential energy at their highest point. Okay, so I can calculate my initial mechanical energy and just subtract my kinetic, not equals plus, okay, plus EK. Now, is there another way I could have done that? I didn't do it this other way because it involved two calculations instead of one. Could I have calculated the maximum height from using projectile motion as well? I could have. And then I would have plugged that in and got m times g times h. Okay. In the end, actually, it's in the end either way is the same. It's two calculations either way. This is my second calculation using this method. Okay. So I'm going to subtract the kinetic energy over. Okay. So I'll take my initial mechanical energy, so that'll be, what was their mass, 56? 56 times 9.81 times 15 plus 0.5 times 56 times 21 squared. Okay, so that's my initial mechanical energy there. And I'm going to subtract 1/2 times 56 times that speed I just calculated, the 19.7 squared. That'll leave me with the initial potential energy. Or sorry, the potential energy, sorry, at the top. Okay, so 56 times. Why did I put the mass back in? Anybody know? If I'm calculating energy, do I need mass? That's why I put the mass back in. I'm calculating an energy, not a height or a speed. Okay, so 0.5 times 56 times. Okay, so that's the potential energy at the highest point. Okay. If I wanted to, I could calculate the height from that. Okay, so their maximum height ends up being 36.7 meters. Okay. So would I do that often, like on a test? No, it's a lot more than you need to do on a test. Hello? No? Yep. Okay, bye. Or someone wants to do your registration. Okay, so does everyone follow what we did there? Okay. It was just more conservation of energy stuff. I just had to do a projectile calculation in order to get one of the values. Okay. Again, I'm not going to combine those two concepts on a test question. Okay. All right. So just so you know what's coming up here, tomorrow we are going to do a lab on energy conversion. So we'll be back with the wooden tracks and the carts and all of that good stuff. Okay, but it's going to be looking at the efficiency of a simple energy conversion of potential at the top to kinetic at the bottom. Okay, super easy thing to do. Probably will get most of it done in class, I would think. Okay, looking at the friction labs, so far so good. Okay, looks like lots of people were really paying attention there. So far so good on those. Okay. So tomorrow, yeah, we'll do the lab. Wednesday, we're going to continue to look at this stuff here. Thursday, will be our unit exam review. Okay, Friday, we'll talk about power. Monday, test. Okay, there's like basically nothing on power on the unit exam except like one multiple choice question. So that's why it's a Friday thing and why it's so little. No, you still have a quiz Tuesday. Yeah, I'll post that at 3:15. Yes, but the lab, like I said, the lab is pretty quick.